Quantum computing is a new type of computing. It harnesses the principles of quantum mechanics. Quantum mechanics is the study of how tiny particles behave. Unlike traditional computers that use bits, quantum computers use qubits. A bit can be either 0 or 1. A qubit can be 0, 1, or both at the same time. This is called superposition. This unique feature allows quantum computers to perform computations in ways classical computers can't. They can explore many possibilities simultaneously. This makes them significantly faster for certain tasks. Imagine searching through a maze. A classical computer tries each path one by one. A quantum computer explores all paths at once. These capabilities open up exciting possibilities. Quantum computers could revolutionize medicine, materials science, and artificial intelligence. However, this power also presents significant risks, especially to our current data security methods. Classical computers have served us well for decades. They rely on bits, which are like tiny switches that are either on, 1, or off, 0. All our data, from emails to financial transactions, are essentially long strings of these bits. Classical computers process these bits sequentially, one after another. Quantum computers are fundamentally different. They operate on the principles of superposition and entanglement. Superposition allows qubits to be in multiple states at once. Entanglement links qubits together in a way that their fates are intertwined, even when separated by large distances. These quantum phenomena enable quantum computers to perform computations impossible for classical computers. Imagine trying to find a specific grain of sand on a beach. A classical computer would have to examine each grain individually. A quantum computer could analyze all grains simultaneously. This difference in processing power has profound implications for encryption, which safeguards our digital lives. Encryption is the backbone of our digital security. It scrambles data, making it unreadable without the correct key. Most online services, from banking to email, rely on encryption to protect sensitive information. Current encryption methods like RSA and ECC rely on complex mathematical problems that are difficult for classical computers to solve. These problems often involve factoring large numbers, which would take classical computers millions of years to crack. However, these problems are not fundamentally difficult. They just take a very long time for classical computers to solve. Quantum computers, with their unparalleled processing power, could potentially break these codes in a fraction of the time. This capability poses a significant threat to our current encryption infrastructure. If a powerful enough quantum computer were built, it could potentially decrypt sensitive data that's been recorded and stored, even if it was encrypted with today's strongest methods. The potential for quantum computers to break encryption is not a distant threat. It's a looming reality that we need to address urgently. Imagine a world where all our encrypted data, from financial transactions to medical records, becomes vulnerable to hackers. The consequences of such a scenario are staggering. Widespread data breaches could lead to identity theft, financial collapse, and even national security threats. The very foundation of our digital society, built on trust and security, would be shaken. The urgency to develop new encryption methods resistant to quantum attacks cannot be overstated. We need to act now to ensure that our data remains secure in the quantum age. This is not just a technical challenge, but a societal one. It requires collaboration between governments, industry leaders, and researchers to develop and implement new standards and solutions. The future of our digital security depends on it.
Thank you for watching, and make sure that you like and subscribe.